At any given moment, thousands of overlapping electromagnetic frequencies, from Wi-Fi signals to broadcast radio, are bombarding your devices in a chaotic, invisible web. The central challenge of electrical engineering is designing a system that can reach into this noise and isolate one specific intended signal. We quantify a circuit's filtering ability using the quality factor, Q. This is the ratio of maximum energy stored per cycle to the energy dissipated as heat. This ratio determines the physical shape of a circuit's sensitivity, seen in these two resonance curves. A low energy ratio results in curve 2, which accepts a broad, inefficient band of frequencies. Curve 1, however, represents high selectivity, a sharp peak that captures one exact frequency while excluding the rest of the spectrum. This high selectivity response is not a matter of chance. It is a mathematical outcome derived from the fundamental properties of the components involved. This equation defines impedance, the total opposition to current. Expanding terms shows opposition is tied to frequency. The inductor and capacitor act in opposite ways. At omega naught, these reactive forces cancel out. The chart shows impedance hitting its absolute minimum, leaving only pure resistance, R. This graph illustrates the consequence of reaching minimum impedance. Because opposition is lowest, the circuit allows maximum current to flow. Moving away from the resonant frequency reintroduces reactance, increasing total impedance and reducing current. At resonance, the circuit's reactive forces neutralize one another, allowing the maximum current possible given the constraints of the resistor. Knowing the peak frequency is necessary, but to gauge selectivity, we must also quantify the width of this response curve. In this graph, we establish boundaries at the half-power frequencies. These are the points where the current drops to approximately 70% of its peak value. The horizontal distance between these 2 points is the bandwidth, represented here as 2 delta omega. To solve for this width, we set the net reactance equal to the resistance at boundary frequency, omega 1. Expanding omega 1, we use the binomial approximation to simplify the inverse term. Complex terms cancel out, leaving a direct relationship for the bandwidth. The physical width of a circuit's response is governed strictly by the ratio of its resistance to its inductance. The quality factor is mathematically defined as the ratio of the resonant frequency to the total bandwidth. When we substitute the bandwidth term with the resistance to inductance ratio we just derived, the formula simplifies. This shows that to achieve a higher Q score, an engineer must either increase the inductance or decrease the internal resistance of the circuit. This equation shows a final alternative form, expressing the Q factor through the specific values of resistance, capacitance, and the resonant frequency. Regardless of the form used, resistance remains the primary limiting factor for a circuit's selectivity. The quality factor is a rigid physical constraint, determined entirely by the component values selected during the design process. This derivation brings us back to the comparison of the 2 resonance curves. Curve 1 is the result of low resistance, which leads to a narrow bandwidth and high sharpness of resonance. In contrast, curve 2 shows how higher resistance widens the bandwidth, lowering the Q factor and making the circuit more susceptible to interference from adjacent frequencies. High selectivity is achieved when a circuit is tuned to maximize its internal energy storage while minimizing the energy lost to its own resistance. This mathematical relationship is what allows a receiver to keep a signal isolated from the crowded electromagnetic environment. By balancing the specific values of resistance, inductance, and capacitance, engineers ensure a circuit responds only to the intended signal, regardless of the noise surrounding it.